So let's look at support vector machines. This is a new learning algorithm. Just to kind of take stock of where we are, we've seen linear models what feels like many centuries ago now, and we've also seen this the recurrent question of how do we know whether a learning algorithm is good or not. One way of answering this question is using the framework of online learning, and you get algorithms like Perceptron. We did not talk about Winnow, but that's another online learner for linear models. We looked at pack learning and agnostic learning, and when this style of asking questions about the goodness of learning algorithm meets linear models, we get support vector machines. Eventually, there are other ways of answering that question. One more a way to answer this question, which we'll look at later in the semester, is a probabilistic perspective from it's the Bayesian perspective. And applying the Bayesian perspective to linear models gives you a learning algorithm called logistic regression. And we'll talk about that, hopefully not too long from now. In this lecture, this unit covers support vector machines, where we're going to frame the problem of learning as that of maximizing the margin. Doing so will give us a certain objective, a learning objective called SVM objective, which is really an optimization problem. And then we'll spend a fair amount of time talking about how do we solve that optimization problem. When we are talking about how to solve the optimization problem, we'll end up looking at a very general strategy for solving optimization problems broadly. We've already seen that. We've seen a version of that, but we'll spend a fair amount of time looking at stochastic gradient descent, which is perhaps one of the most commonly used learning algorithms out there. Along the way, we are going to hit a few important machine learning ideas. The idea that we can frame the problem of learning as an optimization problem by simply defining a certain objective function. The goal of learning is no longer going to be, I need to invent a new learning algorithm. The goal of learning is going to be, I need to invent an optimization objective. Because if we frame it that way, then we can just make the actual algorithmic aspects of learning somebody else's problem, namely the people who invent optimization algorithms. Well, we are going to be the same people today. We'll also look at an optimization algorithm, which is gradient-based optimization. We have seen flavors of this idea already. When we looked at least mean square regression and stochastic gradient descent for that, we'll revisit that idea, spend a bit more time on the optimization part, because that's going to take us to the standard ideas that pervade neural networks and such things. I also have listed kernels and duals and support vectors here, but I'm certain we don't have time to cover that, but that lecture is available online if you are interested. So let's start this process of inventing the SVM objective. For that, we need to look at this idea that of training by maximizing the margin. I'm sure you all remember this thing. I don't. But we've seen this before. We've seen this idea that if we have m examples with high probability, there's some hypothesis H for which the generalization error is bounded by training error plus something here. We don't really care about what that thing is, so let's just put it in a box. The generalization error is bounded by training error plus some expression of the VC dimension. And what we know is lower VC dimension makes the thing in the box small, which makes this whole thing small, which means this thing gets smaller. So a reasonable training, a reasonable strategy for learning is, I would like to minimize the generalization error. I have no idea how to compute the generalization error. Instead, let me make this quantity small. I can make the sum of the training error plus something involving a VC dimension as small as I can. And if I do that just the right way, my generalization error is going to be small. And that's the goal. I can frame the problem of learning that way. We know this, we've seen this before. Another thing that we've seen is with linear classifiers, the VC dimension in d dimensions is d plus 1. So if I have d features, the VC dimension of linear classifiers is d plus 1. This seems like these two statements are at odds with each other. I claim that the goal of learning is to make the VC dimension low. But if I give you a problem, a learning problem that has d features, the VC dimension is fixed to be d plus 1. How do I make that small? Any ideas? Yes.
Cut out features.
That's a fantastic idea. You can, if the number of features is d, and I want to make the VC dimension small, I could toss out some features and I'm suddenly getting a better model. That's called feature selection. Feature selection is a very, very difficult task. Feature selection is a non-trivial problem, except for very easy cases, like what you have in your project, where the training data contains certain features that are all 0 for the entire training set. Might as well get rid of those. But in general, feature selection is a difficult problem. So let's not take that approach. Instead, there's another way to think about this thing, which is, if I claim that the VC dimension of linear classifiers is in d dimensions is d plus 1, does this mean all linear classifiers are the same from the expressiveness point of view? Because the VC dimension is a measure of expressiveness. Let's look at that question a little bit more in detail. And to do that, let's revisit this notion of a margin. Remember margin? We saw that for perceptron, right? So the margin of a certain hyperplane, maybe this hyperplane, with respect to this data set, is simply the distance of the closest point to that hyperplane. Right? We've seen this before. Using the idea of margins, let's try to examine this question. Suppose the only two classifiers that are allowed for this data set are H1 or H2. Importantly, both H1 and H2 have 0 training error. Both of them are perfect. Both of them put all the positives on one side and all the negatives on the other side. Now, imagine that you are a learning algorithm and you have to choose between H1 and H2. Both of them have 0 training error. So the training error gives you no idea about which one is better. But if you have to choose one, which one would you pick? One person. Okay, so there are a few votes for H2. Anyone saying H1? Anyone saying H2? Anyone else saying H2? Yes. H2? And you say H2? A lot of H2s. Can one of your H2s tell me why? There's an H2 on Zoom also. Yes.
Because in an unseen example, there is a high probability that it will be classified correctly.
Why?
Because the margin from the nearest point it has a maximum margin from the nearest point.
Because so the answer is because the margin is greater, and that's also the answer on Zoom. A new example has a better chance of being classified correctly. So maybe if I have a positive example here, will that get classified correctly? Neither of those will do that. So can you refine what you just said? Can you tell me where I can put a point that would be misclassified by H1 but correctly classified by H2? Yes.
I'm just sort of visualizing it. Probably something that's a bit closer to H1 on the left side.
Here?
Yeah, something like that.
Something like that. That point would be somewhere here, and it's on the wrong side of the margin. It's on the wrong side of the hyperplane for H1. It's on the correct side of the hyperplane for H2. Basically, what's happening here is that if you pick an example that has you can't pick test examples. There's a probability that a certain test example might lie on the correct side of the hyperplane, for each of these things. That probability is higher when you maximize the margin with a greater margin, simply because there's a bit more leeway for the examples to show up. There's a bit more gap on the correct side of the hyperplane for H2 than there is for H1. So there's more room for the positive examples to fit in. This is just a hand-wavy argument. I'm not actually proving anything here. I'm just kind of asking you to think about this intuitively. H2 is a better choice, and the formal reason for that is because it has a higher margin. But that's weird, right? It has a higher margin, but both H1 and H2 are linear classifiers in D dimensions, and linear classifiers in D dimensions have a VC dimension of D+1. VC dimension does not seem to tell us anything about whether H1 or H2 is better. And yet, there's an intuition that H2 is better. Can we somehow formalize that intuition? And the answer to that is we can define something, we can extend the definition of VC dimension. Intuitively, larger margins are better. VC dimension is simply a property of a set of functions, right? VC dimension is just nothing, it has nothing to do with linear classifiers or something. It's more about a set of functions. I can ask what's the VC dimension of any set of functions. Now let's consider a set of functions capital H1, all of which every hyperplane in capital H1 has a margin of gamma 1. So it's all linear classifiers that perfectly separate the data with margin gamma 1. It's a set of functions. H2 is another set of functions. All linear classifiers that perfectly separate the data with margin gamma 2. And let's say gamma 1 is bigger than gamma 2. Meaning every classifier in capital H1 has a larger margin than any classifier in capital H2. Capital H1 consists of all functions that look like this. I see that I have now messed up the 1s and 2s here. And capital H2 contains all functions that look like that. It's a set of functions. The claim is it's not just the single hyperplane with a larger margin that's better than a single hyperplane with a smaller margin. The entire set of functions with larger margins is better than the entire set of functions with a smaller margin. The entire set of functions H1 is quote unquote better. What does better mean here? We can formalize this using the notion of VC dimension. And that's what Vladimir Vapnik did with this here. If you have a set of functions that separate a training set with a certain margin gamma, that's the set H. Then the VC dimension is, we know that the VC dimension of all linear classifiers is D+1. But what Vapnik showed was actually the VC dimension of this particular subset is going to be less than, it's not just D+1, it's the smaller of D+1 and R square over gamma square plus 1. The VC dimension is going to be less than that quantity. It's going to be less than the minimum of 1 plus R square over gamma square or 1 plus D. Where R and gamma are exactly the same things that we saw in the perceptron case. R is simply the radius of the largest ball that contains all the data, and gamma is the margin of the data. We're back to R square over gamma square, which somehow I feel very happy when I see this, because it tells you that R square over gamma square is a quantity that shows up independently in different ways of analyzing this problem. The size of the data and the margin of the data are important complexity parameters. And notice this thing here. As R increases, the VC dimension can increase as the data gets bigger and bigger because this quantity increases. More importantly, as gamma increases, the VC dimension decreases. When the margin gets bigger, the VC dimension gets smaller. When the VC dimension gets smaller, the generalization error gets smaller. So the goal of learning now is, rather than worrying about all this VC dimension stuff, find a linear classifier that has the largest possible margin. Because the largest possible margin that separates the data perfectly and has the largest possible margin, because then you'll be minimizing this data-driven VC dimension. As a result, you'll improve generalization. That's the philosophy of the support vector machine. We are out of time, but I'll just wrap up today's lecture with this refrain. Larger margin gives you lower VC dimension. Lower VC dimension gets you better generalization bound. So larger margin gives you better generalization, which means a goal for learning can be to maximize the margin. All right, we'll stop here. On next Tuesday, we'll take this idea and we'll set up an optimization problem that seeks to maximize the margin. Don't forget your project submission if you have not done it already.